Section 2 of Chapter 9 discusses confidence intervals for a mean when sigma is unknown. In most sampling situations, the population standard deviation, sigma, is not known. So you can read this in slide 14, these examples. But most situations, we have no idea what sigma is. So when we don't know what sigma is, we use what is called the t-distribution instead of the standard normal distribution to calculate probabilities or to calculate t-values, which are equivalent to the z-values we found before. Like the z-distribution, the t-distribution is continuous. Like the z-distribution is also bell-shaped and symmetrical. And in the middle you have 0, 2. There is not one t-distribution, but rather a family of t-distributions. All t-distributions have a mean of 0, but the standard deviations differ according to the sample size. The t-distribution is more spread out and flatter at the center than the standard normal. As the sample size increases, however, the t-distribution approaches the standard normal distribution. So this one in green is the z-distribution we used before. And the t-distribution is flatter, but as the sample size increases, this distribution becomes narrower and narrower until it matches the z-distribution at very large sample size. Comparing between the two. In the z-distribution at 95% confidence, when we use a confidence level of 95%, the value found was 196 and minus 196 here. But if we use a t-distribution with a sample size of 5 items, which is very small, the same 95% confidence or area in the middle will yield a value of 2.776 here, or minus 2.776 here. And you read those values in the table called student t table or t distribution. In a moment we'll see that. For example, a tire manufacturer wishes to investigate the tread life of its tires. A sample of 10 tires driven 50,000 miles revealed a sample mean of 0.32 inches of tread remaining with a standard deviation of 0.09 inches. So in the problem we get n is 10, the sample size. The average obtained is 0.32. We don't need to calculate it. The standard deviation is 0.09. Construct a 95% confidence interval for the population mean. Would it be reasonable for the manufacturer to conclude that after 50,000 miles, the population mean amount of tread remaining is 0.30 inches? Well, now we need to develop or compute the confidence interval using the t-distribution, due to the fact that sigma is not known. And the confidence interval it's exactly the same we saw before in the previous section. Is x bar plus minus, instead of z, this is t, times s instead of sigma, divided by the square root of n. So we use this, the only standard deviation that we can use, which is the sample standard deviation. This is a copy of the t-distribution table. Since we're using the 95% confidence, we just look at the top of the table, find 95, that's 95. And then on the degrees of freedom, we look at n minus 1, the sample size minus 1. Since the sample size is 10, 10 minus 1 equals 9. So go down the degrees of freedom, stop here at 9 degrees of freedom, read across and stop right under the 95% confidence interval. If the confidence interval were 98, then you stop here and read 2.821. If it were 90%, then you read 1.833 for the same degrees of freedom. So in this case, the t value is 2.262. This is equivalent to our z value before. And it is here to the right and here to the left, plus minus. So what is a confidence interval? X bar plus minus t times s of the square root of n equals 0.32, the sample mean, plus minus 2.262 times, this is the t-value, 0.09, the s value, the standard deviation of the sample, divided by the square root of the sample size, the square root of 10. If you do that, then you get 0.32 plus minus 0.064. That means if we do this sampling, we just took one sample. If we do repeated samples, 95% of them will include the population mean. In this case, one sample yields this range. And that is, if we add 0.064 to 0.32, that's 0.384. If we subtract 0.064 from 0.32, you get 0.256. And if you notice, the last question, is the thread 0.30 reasonable? Well, apparently it is, because the range at 95% confidence is between 0.256 and 0.384, and 0.30 is between the two. This is another example. The manager of the Inlet Square Mall near Fort Myers, Florida, wants to estimate the mean amount spent per shopping visit by customers. A sample of 20 customers reveals the following amounts spent. So these are the amounts spent. Based on the 95% confidence interval, do customers spend $50 on average? Do they spend $60 on average? Well, in this case, you can use Excel, and I copied these values here into Excel file. Okay, so these are the same numbers. Step number one in this case is you just need to go to data analysis, and then use descriptive statistics. Okay, click OK. Select the data set first, that is right here on top, input range. Output range, you can select, let's say, right here, and check summary statistics. And in this case, we're going to check also confidence level for mean. Notice at 95%, you change this if the confidence interval is different. So since 95% is used in this example, we check 95%. Click OK. And you get your mean, 49,348. You get your standard deviation of the sample. Remember, Excel by default calculates sample statistics. So remember the formula, the mean plus minus the margin of error. The margin of error will be, let me put it here, mean plus minus the margin of error, which is equal to x bar plus minus the t-value times s times the square root of n. We get this, and with that, we know that. I mean, we calculated this and this using Excel, and we know the n, the sample size. We don't know t yet. But notice in Excel, you get 4.22 approximately. Well, that is the margin of error that given directly to you, so you don't need to make any calculations. Okay, so you will get, what is the average confidence interval? 49,348 plus minus 421, and that is approximately a range of like a 53 maximum, 53 point something, and a minimum 45, 44 point something. Okay, so that is the confidence interval. And here is the solution using every step, every calculation. The t-distribution is used to calculate the 2.093. Let's try to find that using 19 degrees of freedom. Let's look at the table again. This is the table. Now this is a copy from the book on appendix B.5 or B.5. Remember, this is found at the end of the textbook in End Matters section. That's where all the appendices are. All right, 95% confidence and 19 degrees of freedom. 2.093. 2.093. Okay? 2.093. Now in Excel, you can also calculate a t value by using this, equal t. But then, once you type t, notice all the options that I have, I need the inverse case. Inverse always, the inverse command always find the t value, and in the case of z, a z value. Okay, and we are using, notice that it's asking me for either inverse, it says here returns a left tail inverse, in other words, a t-value using probabilities to the left. But I want to use the confidence interval, so I choose 2t. In other words, I need to provide Excel here the information on the two tails. Well, my two tails together are equal to 0.05. It's asking me first for the probability. Those are my two tails. Comma, and then the degrees of freedom, 19. Close parenthesis, and then hit enter. Notice 2.093, same value. Okay, so the endpoints of the confidence interval are 45.13 and 53.57. The conclusion is, it is reasonable that the population mean could be $50 because it's between those two. The value of $60 is not in the confidence interval. Hence, we conclude that the population is unlikely to be $60. And these are commands related to Excel and Minitab. I just showed you this one. It's normally distributed. Notice here, if the values of X are normally distributed, then we ask the question ourselves, is the population standard deviation known? Well, if we don't know it, we use the t-distribution. And if we know the standard deviation, we use the z-distribution. All right, that is very important. Please keep that in mind. And the two confidence intervals are x bar plus minus z times sigma of the square root of n. This is when we know sigma. But if we don't know sigma, then we use x bar plus minus t times s over the square root of n. And that's the end of section 2.